Okay, so let's take a look at our paper here real quick. Hopefully you had a chance to, oops, don't want to do that. Hopefully you had a chance to look at these problems. We'll look at those in a minute. So I'll start up here with radioisotope. And I want to point out I do have a slight typo right here. And we'll look at that in a minute. But anyway, what the heck is a radioisotope? Well, let's take a look at the word radio. So the word radio is looking at radioactive. Okay, so what is something that's radioactive? So we see that on movies and things like that, radiation. So what radiation is that if you have something that's unstable, so we've got this unstable element here. And what happens is that particles are going to break off of this unstable atom until it can get to a situation where it finds that it is stable. And so those particles can be all kinds of things. So we could have neutrons. So neutrons are pretty common. So you can have a neutron. You could have an alpha particle. So a 4,2 helium is what that looks like. You could have a beta particle. So like a beta particle would be look like that. You can have another atom of something else. But what happens is these pieces in radioactivity break off, and you can also have gamma rays. So gamma rays are things that are dangerous to living things. And so these things can kind of break off, and we can use this radiation to do various things. So we can figure out how old something is by looking at different ratios. We can get rid of bacteria or cancer cells, or we can do imaging inside the body. So a lot of different things can happen from this idea of the breaking down of the decay. All right, so radioactive, and an isotope means that these are items that are have different masses than maybe they normally would. So, okay, so let's take a look at our definition. So a little error here. It says when and, I need to fix that. So let's cross that out and say when an element contains either too few or too many or too few neutrons. And so your first blank there is going to be neutrons. So I'm kind of trying to squeeze that in there. Then it is going to be unstable. Okay, so unstable and radioactive, these are the same thing. So when it has too many or too few neutrons, then it's going to be, and actually probably could put both words in there. It's going to be radioactive. And then let's go ahead and also put in there unstable. So fit those in that blank there. And so when things are unstable, so going back to our original idea here. So this guy here, that was unstable, and then it broke down into these other pieces in order to try to become stable. So it was unstable initially, or radioactive. So what happens, it spits out pieces, things break off, and it keeps doing that in order to stabilize itself. So it wants to change to a more stable nucleus by giving off that radiation that we were talking about. So by getting off radiation, it becomes more stable. So what does IB want you to know? IB wants you to know that radioisotopes are useful, but remember, IB is kind of this world multi-discipline thing. So looking at caring for the world, caring for each other, learning through multiple disciplines. And so radioisotopes are very useful. They have important uses for medical diagnosis, medical treatment, and research, but they do pose a danger to living things. So that thing right there at the end, they do pose a danger to living things, is kind of the key thing. So you have something that's useful, but something that can be dangerous. So if we come over here, these came right from your These are right from your IB textbook. That the PDF is in Schoology. So right here. So radioisotopes are used in nuclear medicine. All right. So what does that look like? So you have something that they need to look internally in your body, and they can give you a chemical cocktail, and then they can image your body, and the imaging system can pick up on those tracers that they put in your body. Where are they located? Or it can help image internal parts of your body, so they can look at organs, things like that. And so they can track the chemicals, or the chemicals can be used to illuminate the inside. So instead of cutting you open and looking, they can just use the image and look, and they could see what's going on inside. Other things, research, chemical clocks, geological and archaeological dating. And so that's the thing that IB does. You have to know what a radioisotope is. You have to be able to give, and here's a big hint, you have to be able to give an example. And here are the 1, 2, 3 examples. I would stick with 1 or 2, and you're going to need to be able to give one of those on the test. And that is a test question. So on the test, we do want to be able to give one of these examples. So we've got radioisotopes, and so like I said, IB is very, very silly, and they really limit it to just a couple of things. So let's take a look here. Carbon-14 dating. So all living things are made of carbon, and so all living things have a ratio of carbon-12, which is the normal carbon, to carbon-14. There's a ratio. So while you're alive, there's a ratio. So when you die, that ratio is going to change, because the carbon-14 is going to decay at a different rate than the carbon-12. So they can use a mathematical formula. They can look at the ratio, and they can figure out how old something is. So you go in your backyard, and you're kicking things around, and you find a bone, and it's pretty big. So you think maybe it's a dinosaur bone. So you're thinking, oh, dinosaur bone, I'm going to sell that for some big time money. All right. So what you do is you take it, and they do some research on it, because they're not going to pay big money for your dinosaur bone unless they know how old it is, that it is a dinosaur bone. And then they run the ratio of the carbon-12 to the carbon-14, and they figure out your dinosaur bone is actually just a bone that your dog buried in the backyard. So it's probably like a a bird bone, or another dog's bone, or some other bone, human bone. Who knows? But it's definitely not a dinosaur bone. So you don't get the big payday, and that is super sad. So anyway, so carbon-14 dating, they've actually used this to look at forgeries. So somebody has a forgery, they can look at they can take a tiny piece of a painting or whatever, and they can figure out how old it is, and then they can tell if it has been forged, things like that. So, all right, other one, cobalt-60. So carbon-14, cobalt-60. Cobalt-60 is used to kill things off. So it is kind of a more of a deadly radiation. And so by giving off the gamma rays, what happens is that the cobalt-60 can kill things off. So that can be cancer cells, so like radiation therapy. But it also can be they can run pallets of equipment past a cobalt-60 sample, and then that radiation that's coming off of it can kill off bacteria and things like that, so that you can sterilize things. They actually use radiation to kill things off, like on berries and things like that they ship. The radiation doesn't stick; it just kills the things, and then so they can kind of pass it through a conveyor belt. So anyway, a couple of examples that you could use. And then radioisotopes also used in PET scans, and so there's different things that you can use for scanning. So I put a scanning item in the notes, and so something that hopefully you don't ever have to to have an experience with, but sadly a lot of us do, is when somebody has a cancer of some variety, then when you do radiation therapy, what you're looking to do is remove the cancer. So if you look on this, the left, these darker spots here, those are the cancer. And so you can kind of see that the imaging picks up cancer in lymph nodes, organs, etc. And so then after going through a treatment, then what you want is you want the good news. And so if you were in this situation, then this is the before, and then the other one is the after. So this is the before, and then this is the after. And so this is good news for this individual, because you can see the massive reduction in the cancer cells over here. All of these problematic areas, these dark areas, are gone. And so that's great news for this person, because maybe this cancer is in remission or it's been eliminated. And so that's the kind of imaging that they can do. So, okay, let's take a look at your chart here. Let's see how you did, and I'll go over it with you. This is basic stuff. So proton's bottom number. So here we go. We're going to go with 92. Okay. So when you're looking at these things, top number minus bottom number. And so when we're going through these, you just want to know these patterns. I mean, you learn these in 10th grade, right? I think I literally just taught them to my 10th graders a week ago. So if you think of it as like 235 minus 92, then that's going to get your neutrons. So we're going to go with 143. And the electrons are the same as the protons because there is no charge. So 92. Okay, this one right here, well, still uranium, so it's still 92. But this is an isotope. So these two are isotopes. See, they have different masses, and so those are isotopes. So those are isotopes, isotopes of uranium. Maybe that's what we should write down. So these are, these would be isotopes of uranium. And so the difference here is, instead of the 238, this one's a little bit heavier, 146. But still 92 electrons because it doesn't have a charge. Now this one, this arsenic here, going to be a little bit different. So let's switch colors here. So we got 33 protons. Okay, so then 75 minus the 33, so 42. But the electrons, how do I figure electrons out? So the key is to look at the minus 3. And you got to think, is that 3 more or 3 less electrons? Well, minus 3 is 3 more. So I tell my kids, do it like an opposite. So I would look at the 33, and then instead of minus 3, I do the opposite, plus 3. So that, of course, is going to equal 36. So 36 electrons. Now, if you want to check yourself, protons minus electrons should equal charge. So that is indeed -3. And the last one, you got to come up with the symbol, and I'm going to do it over in the corner because there's not enough space there. So let's do it over here. Let's go 17 on the bottom. Right, so that's 17 protons goes on the bottom. So I'm going to add these two. I'm going to add those up to get the mass number. So 17 and 20 is 37. Now we got to look up number 17. We got to figure out what it is, right? Because if you don't have, so you can look up number 17 on your periodic table, and so you're going to find that it's going to be chlorine. Okay, so right there, number 17. Let's come back over here and drop chlorine in. And then it has 18 electrons. So remember, protons minus electrons equals charge. And so we'll put a minus sign right there. So there we go. there is your chart. Should be able to do that, guys. That is pretty easy stuff. But I think key thing is recognizing the ones that are isotope